To the naked
eye, the night sky presents an illusion of absolute permanence. The stars appear fixed, but in reality, nothing is stationary. When observing the constellation Serpens, one particular orange dwarf star known as Gliese 710 captured the attention of astronomers for a very specific reason. Over years of observation, it appeared motionless relative to the stars around it. When a star fails to drift across our two-dimensional X and Y field of view, basic geometry leaves us with exactly two distinct possibilities. The star is either perfectly synchronized with Earth's orbit, or it is moving directly along the invisible z-axis of space, straight toward the observer. Tracking a star moving laterally across the sky is a straightforward process. Calculating the velocity of an object traveling straight down the invisible line of sight requires an entirely different set of mechanics. Gliese 710 was never hovering in place. Its lack of lateral movement was the earliest mathematical indicator that it acts as a cosmic projectile on a direct path toward our solar system. To measure that hidden z-axis motion, astronomers needed sensors far above the distortions of Earth's atmosphere. In 1989, the European Space Agency initiated the Hipparcos mission. Hipparcos was designed as a dedicated astrometry tool capable of calculating precise stellar distances and mapping the galaxy with a level of accuracy unattainable from the ground. But the launch suffered a critical failure. A malfunctioning thruster prevented the telescope from reaching its intended safe position, leaving it trapped in a highly elliptical orbit. That massive fluctuation in altitude forced the delicate satellite to plunge directly into the deadly Van Allen radiation belts 4 separate times every single day. The relentless bombardment of high-energy protons systematically destroyed the onboard electronics. By 1993, the telescope was entirely offline, reduced to orbiting scrap metal. Yet in those 4 years of operation, Hipparcos successfully captured precise data for over 118,000 stars. It secured the exact mathematical dataset necessary to reveal the trajectory of Gliese 710 by the end of the decade. In 1999, scientists began parsing that massive dataset to answer a highly specific question. How fast is a star 62 light-years away traveling along the z-axis? The answer relies on the quantum mechanics of spectroscopy. As photons travel outward from a star's photosphere, specific elements in its atmosphere absorb exact wavelengths. This diagram shows the resulting visual signature. The absorbed light creates missing wavelengths that appear as stark black gaps, forming a distinct chemical barcode. Because Gliese 710 is hurtling toward our telescopes at 14 kilometers per second, incoming light waves are physically compressed. This compression causes the entire barcode pattern to shift toward the blue end of the spectrum. Measuring that exact degree of blue shift provided the absolute mathematical proof of the star's velocity. The data revealed two critical facts simultaneously. It proved the speed of the star's approach, and the specific arrangement of chemical lines identified Gliese 710 as a stable K-type orange dwarf. There are no gravitational anomalies or mysterious deep space events propelling this star toward our solar system. The mechanics are entirely standard. Our own sun currently orbits the galactic center at a speed of roughly 220 kilometers per second. The Milky Way operates on the principle of differential rotation. The galaxy is not a solid spinning disk. It functions like a massive multi-lane highway where stellar objects move at slightly different relative speeds. Tracking our sun and Gliese 710 within this galactic model reveals that while they orbit in the same general direction, their individual speeds are mismatched. This kinematic mismatch means Gliese 710 is drifting into our orbital lane over millions of years. There is no deliberate aim behind this trajectory. It is simply the predictable geometry of gravity and momentum playing out on a galactic scale. Projecting this geometry forward yields a very precise timeline. Gliese 710 will arrive at our solar system in exactly 1.3 million years. The star will not physically strike our sun. It will pass at a distance of approximately 0.16 light-years, which is just over 10,000 astronomical units. 0.16 light-years places the star directly inside the Oort Cloud, the vast spherical shell of dormant icy bodies surrounding our solar system. As Gliese 710, with 60% of our sun's mass, plows into the outer edge, it carries a massive sphere of gravitational influence. Passing through the cloud, that immense gravitational pull will violently destabilize the orbits of millions of dormant comets. The physical star itself will pass by without contacting the inner planets. The actual danger lies in the relentless meteor and comet shower its gravity will send plunging inward toward Earth. A massive cometary bombardment is a severe planetary hazard, but evaluating this event on the scale of deep time changes the equation. The spectroscopy data from Hipparchus confirmed that Gliese 710 is a K-type main-sequence star. K-type stars offer immense biological value. They emit very low levels of harmful UV radiation and possess an incredibly stable lifespan, capable of burning steadily for 15 to 70 billion years. Our sun will naturally expand, threatening life on Earth billions of years before the incredibly stable Gliese 710 begins to run out of fuel. 1.3 million years is a vast interval for technological and biological evolution, far exceeding the total history of modern humans. If our distant descendants persist, this intersection provides an interstellar lifeboat, a long-burning stellar engine delivered to our doorstep by the same orbital mechanics that define the galaxy.